Okay, so this is our lecture number 8. Last week we have missed one lecture. And again, we are in module number 1. And today we are going to complete our module number 1. And module number 1 is review of MOSFET operation and fabrication. So in this particular module, what we are going to learn? We are going to learn novel MOSFET architectures. In last lecture, we have started with novel MOSFET architecture. So what is meant by novel MOSFET architecture? Means which is different from conventional MOSFET or conventional MOSFET architecture. So what you see here, we call this architecture as conventional MOSFET. It's a planar MOSFET. Then in last lecture, we have seen FinFET. Here there is only one gate and control is only from the top. But if you see, this is called as FinFET, which is called as novel architecture. This is very thin pin and gate is from both the sides. So therefore, control of the current is better as compared to MOSFET. But again, there are limitations of FinFET. That's why can't we have gate all around the channel? So that is called a GAA channel MOSFET. Then this is limitation of silicon, because silicon you cannot scale to a very, very small dimension like 1 nanometer or sub 1 nanometer. So therefore, people are looking for new materials, and one of the material is carbon nanotubes instead of silicon. So can we go with carbon nanotubes? So that we are going to learn in this today's lecture.
Yes.
So what is the objective of lecture number 8? So first is to understand structure of MOSFET, which MOSFET, but that is gate all around FET, that is field effect transistor, and which is also called as GAA FET, field effect transistor. Then its working and its advantages. At the same time, we are going to know what is the structure of carbon nanotube, FET, and its working and its advantages. Okay. Then after completion of this lecture number 8, so what you will know? So you will be able to draw structure of GAA FET and CNT FET. GAA FET means gate all around FET, and CNT means carbon nanotube FET. Then you will be able to explain working of GAA FET and CNT FET. And you will be able to explain advantages and disadvantages of GAA FET, that is gate all around MOSFET or FET, and CNT FET, carbon nanotube FET, over conventional MOSFET. So let us start. So why we are going for novel MOSFET architectures? That is the question. And as you know that in last lecture also you have seen, this is MOSFET structure. And as we scale MOSFET, this is source and this is drain. They are very close to each other. And therefore gate loses the control. And then there is a leakage current. That is one reason. Then we call as a short channel effects. There are various short channel effects like debel, tunneling currents, then leakage power. So many short channel effects, velocity saturation. Then reliability issues are also there. That is hot carrier effect. So therefore, now people are looking for some new architecture. And we have seen FinFET is one of the new architecture. And right now, 12 nanometer, 40 nanometer, and even cell phones, whichever they are having processor, that is using FinFET, not bulk MOSFET, but most of the processors which are used in cell phones are FinFET. Then again, there are limitations of FinFET. So this is FinFET, what you see here. It's a double gate MOSFET, sometimes we call. And therefore, now instead of having gate from two sides, can we have gate all around channel? So if there is a gate all around channel, means gate is controlling flow of electrons or charged particles from source to drain. Yeah, and its control will be there from all the sides. So therefore, better leakage current means very low leakage current and high saturation currents. So that's the advantage one can get from gate all around MOSFET or FET. Now this is another structure. Like a pin, there can be multiple pins. There can be such nanowire. Sometimes it is called as nanowire. It's very, very thin, or its diameter is just 1 or 2 nanometers. And gate is all around or wrapped around that nanowire. And that gives us MOSFET, novel MOSFET architecture. We call that as a GAA FET. And right hand side, you can see here, this is your drain, this is your source, and just this is gate. Whatever you see, this gate is wrapped around that nanowire. This is called as nanowire. Whatever you see, this is cross section. This is isometric view. This is also isometric view. And if you take cross section, so whatever you see inside, that is just nanowire. Then around that there is oxide. We call that as gate oxide. And over gate oxide, we deposit or we put some material, that is conducting material. So since gate you see all around channel, so that's why it is called as GAA MOSFET. Right?
Yes, sir.
Now let us see how it is fabricated. So there are various types of GAA FET, various types. So here I'm showing just fabrication process flow for gallium, indium gallium arsenide channel GAA FET. So see, first we take highly doped P-type Indian phosphate, that is a substrate. Then over that, in P-type, lightly doped P-type indium gallium arsenide is deposited. Its thickness is around 30 nanometers, right? Then N plus source and N plus drain are doped. See here, N plus source and N plus drain. Okay, so here this is P-type material. Just see P-type material. And in that, with any process, maybe diffusion process is not here, but ion implantation. So we just change this selectively, this much conductivity to N plus, this much conductivity to N plus, and we call that as N plus drain and N plus source. Then next is, you see, there is substrate. So using some etching process, the substrate below this channel. So this is channel, you can say whatever is yellow portion, below that there is a channel. So that is east away. So this much portion is east away. See here.
Yes, sir.
Can you see it's east away? So now this pin, what do you say, this much portion is hanging. You can see just it is what
So half
connected to source surface. Below also there is a space, right?
Yes, sir.
So then this is result. Fourth is the result of that etching process.
Okay, like it's totally space length. Okay.
Yeah. And then insulating material is deposited. Okay. So when you deposit insulating material, so insulating material will come. That is basically oxide. We call that as oxide insulator, gate insulator. And that gate insulator will come from all the sides, right? From all the sides below and this one.
Yes, sir. Yes.
And then we put some conducting material on that insulator oxide. And then from everywhere, if you take contact, then that contact is everywhere, because from top as well as bottom is all around.
Sideways also. Yes.
So in this way, you get all around gate. Okay, so in this way, there is a simple fabrication flow. So it looks very simple fabrication flow, but it's very complicated, because such floating structures, to create such floating structures, suspending structures are difficult, but they create. This is not unique process flow, to fabricate GAA MOSFET, there are various processes, but I have shown one by which one can fabricate GAA FET.
Yes, sir.
Now, there is another type of this one. See, this is a double gate MOSFET, you can see. So gate is from this side and this side. So when you take cross section here like this, so what you see, so this is channel basically, whatever is this portion. This is top gate and this is side gate, right? And this is your pin, substrate, insulating material. But what about the gate all around a MOSFET? So it looks like this, but when you take a cross section, you can see here, this oxide is everywhere. From bottom also this oxide is there. From this side also there is oxide. Means gate is all around. It's basically square portion. Sometimes it is a nano wire with diameter, but this is what thin, having a rectangular shape. And from top, from side, back side, and from
Gate is
bottom, there is a
yes.
gate. So that's why it is called as all around gate. Right. So what are the advantages of this one? Because working principle is same, whether it is CNT FET or whether it is MOSFET. So when you apply some field or when you apply some electric field to gate, electrons from source will enter into the channel, and there is a drain field. That drain field will collect those electrons, or in general we can say that the drain will collect the charged particle, and thus when we apply gate voltage, MOSFET is turned on. But we are talking about the control here. Now see here, on x-axis there is gate voltage, and on y-axis there is a drain current. So whatever is this dotted portion means, not dotted, but it is continuous line, this one. So you can see here, this is a continuous line. And this line means what basically gate all around MOSFET. So this dotted portion is of gate around MOSFET. So you can see here, this is double gate and this is double gate. So same voltage is applied. VDS is 0.1 volt. Here VDS is 0.1 volt and gate voltage is 1 volt, and GAA gate voltage is also 1 volt. And this is called, when it is minus 1 volt or when it is this one. So you can see here, this you can say leakage current. So leakage current is very less in case of GAA MOSFET. Even if you increase, gate drain to source voltage to 1 volt, there is not much change in this one. From this to this it changes. But if you see double gate MOSFET, so when double gate MOSFET drain to source voltage is less, this is your leakage current. And when you increase drain to source voltage to 1 volt in double gate MOSFET, that current increases this much. So what you can say, here it is mentioned, transfer characteristics means gate and drain current. So it's double, drain induced barrier lowering effect is more, and that's the reason op current is more in case of double gate MOSFET, but while it is less in gate around a MOSFET. The reason is that gate is wrapped around entire channel, so therefore control is better. Then transconductance, GM, you might have heard about GM. GM is change of drain current with respect to change of gate voltage.
Gate voltage,
and it should be high. The reason is that gain of MOSFET depends upon the, or speed of MOSFET or the device depends upon value of transconductance. And you can see here, double gate MOSFET, its transconductance is less. But when for gate all around MOSFET, so this is dotted portion, it's high. So that's why you can say
more than double gate.
Yeah. So here it is mentioned, transconductance GM characteristics of double gate and MOSFET. GAA MOSFET have higher transconductance. And here it is a performance comparison. Here performance of both the MOSFETs is compared. One is a double gate MOSFET and other is GAA MOSFET. Threshold voltage is approximately same, 0.16, and this is 0.58. Okay. Then subthreshold slope. This subthreshold slope should be as low as possible. So in case of double gate MOSFET, it is 85
Yes.
millivolts per decade, but here it is 78 point this one. So it is less. So therefore GAA FET is better.
Okay, sir.
Then double drain induced barrier lowering. You can see means impact of drain on leakage current.
Yes, very high.
So it is very high, 125. But if you see GAA MOSFET, it's very low. So that's the reason op current is less. Now we want on current as high as possible. Why? Because your speed will be more, performance will be more, gain will be more. And if you see for same voltage, it's 2.96, while GAA FET, its on current is 3.5 milliamperes per micrometer, which is more as compared to DG FET.
Okay.
And op current in DG FET, that is double gate MOSFET, is 2.77 nanoamperes per micrometer. But in case of this one, it is 0.391 nanometer.
Negligible, not
Yeah, means you can say that op current is better. It's
zero,
less.
is best.
Therefore, power dissipation means what? Leakage power dissipation.
Leakage power is less.
Yeah, leakage power is or standby power is less in case of GAA FET. But see, we have seen GA FET, so scaled MOSFET. But what happens? We can, it is what predicted that we can go with silicon material up to 10 nanometer, or might be with 5 nanometer. But if you go below 5 nanometer, so silicon material will not give us a better performance in terms of on current and off current. Off current will be large, so it will lead to very high power dissipation. And because of velocity saturation and other effects, your on currents will be less. So it will not give us any advantage of scaling below 5 nanometer. And therefore now everyone is looking for some other material for the MOSFET instead of silicon material. And some people say that carbon nanotubes may play a very crucial role to replace silicon material. So let us see what it is. So what is carbon nanotube? Why it is? Because as size becomes smaller, scaling the silicon MOSFET becomes harder, as I mentioned. Then requirement of high performance channel material. Silicon material will not give us very high performance. And mobility degradation is one of the impact of scaling MOSFET. And therefore, one is looking for other material. So like CNT FET, carbon nanotube FET. So what are the advantages? So 1D ballistic transport of electron and holes. Now ballistic transport means you might have seen that in conventional MOSFET, on current depends upon velocity of MOSFET. And it increases linearly, and once it saturates. But ballistic means ballistic effect. So in that, velocity of charged particles like holes and this one becomes very high at some particular voltage or particular field. Okay, that is even beyond velocity saturation. And when that effect is there, ballistic effect is there, those high velocity electrons are collected by the drain, and therefore CNT FET will give better performance as compared to normal MOSFET. So that is the reason high drive current and large transconductance. And carbon nanotube is very robust. Basically, carbon material is very robust. So therefore, it will give us a better performance at very, very high temperature. Why? Because their covalent bond is very strong. Covalent bonds are very strong. So you might have heard that carbon material is very strong, very strong.
Yes, sir.
Now, what is the ideal material? So carbon nanotubes were discovered by Lijima in Japan, 1991. Okay. So CNT PET or CNT, carbon nanotube, is just thought of rolled sheets of graphene material. Graphene.
Okay.
It's a graphene
Fine.
material. Okay. So
Yes,
it's
yes.
1D. We consider that as a 1D sheet, and it's a rolled off. So just it's a rolled off sheet here. It's shown here.
Okay.
Electrical properties depend on chirality and direction of this distortion. So how you make nanotubes, it depends upon its properties. So CNT plates, CNTs, carbon nanotubes can be metallic or semiconductor material. Okay. So it's basically very, very thin sheet of graphene material, which is rolled off. Okay. With diameter of 1 or 2 or 5 nanometers. And it's very robust. So that's basically graphene sheet we can create or we can fabricate CNT plate. So based on geometry, there are 3 types of CNT plate. One is called as top gate, other is called as bottom gate, and then coaxial gate plate. Based on operation, there is a Schottky barrier and there is a MOSFET like CNT. So we'll see this. Okay, what is bottom gate CNT plate? So this was the first CNT. See, in 1991 means it was recently this plate
Yes, sir.
was discovered. While this MOSFET was discovered in 1956, and till more than 60 years we use same structure, but now there is a time to replace it because it is not giving us advantages. So one possible architecture is CNT plate. So one is Schottky barrier and other is MOSFET like operation, and this is bottom. In 1998, this first was fabricated. This was the first MOSFET. So what it is a back gate, you can see here, and this is on silicon oxide material. Silicon oxide. 2 contacts are made here. This is one metal contact and another metal contact. And with the help of solution, carbon nanotube is formed, and that carbon nanotube is attached here to these metal contacts. You can see here drain, and this is source.
Yes,
and this is the back gate. This is metal contact, and this is oxide. So here we apply potential, and currents are collected. Drain collects the current, and this is CNT plate here. So this because of this material, this gate voltage, one can control the flow between source and drain. But this was very crude device. It was not very good. So here it is mentioned. It's op current was on state resistance was very, very high. It was having very low transconductance, and there was no saturation current. Yes, if you increase drain voltage, drain current was increasing, and that we don't want. Okay. And therefore, then there was improvement. Now this is called as top gate CNT plate. This is improved performance. So this structure gives a better performance as compared to previous one. Okay, so if you see here, so this is substrate doped silicon material, then insulator is put, then this is source contact, this is drain contact, and whatever you see is your carbon nanotube. On that carbon nanotube, there is a gate dielectric, and this is your top gate. Okay.
Dielectric is?
Top gate.
Okay, that is also connected.
Top gate. So that's why it is called as top gate CNT plate. Now there is another coaxial gate. So what is coaxial? It is like a wrapped around gate or gate GAA plate. But in GAA plate, this is silicon wire. But here it is what? CNT, that is carbon nanotube. Okay. And why this is better? Because there is an electrostatic control over the entire channel. This is source, this is drain. Now, working principle. So as I mentioned, working principle is same as that of MOSFET. So in MOSFET, electrons are supplied by the source and drain terminal will collect these electrons. In other words, current is actually flowing from drain to source terminal. Electrons are flowing from drain to source, source to drain, but conventional current is always opposite to electron current. So actual current is flowing from drain to source. And if you change the gate voltage, current flowing through MOSFET will change, because if you put more gate voltage, more charge is created in the channel and your current is proportional to the charge. Now what happens in SB CNT FET? So SB means Schottky barrier. Schottky barrier means basically there is a junction between this carbon nanotube and this source. Source is metal. Okay.
Yes.
Drain is also metal.
It's a metal.
Yeah. So it's so in Schottky barrier, actually how current flows in normal MOSFET, electrons cross the barrier, that is source and channel, and they enter into the channel. But in case of Schottky barrier, electrons will not cross the barrier, but they will tunnel through the barrier.
Okay.
Because of the and
because the magnet field.
Earlier I told you that what is tunneling.
Yes.
So therefore, at low gate bias voltage, large barrier limits the current in the channel. Means therefore its characteristics are better. Means its op current is less. Why op current? Because if gate voltage is low, there is a barrier, and because of that barrier, electrons cannot jump that barrier. But as you increase the gate voltage, then in the barrier there will be some states, electronic states, that is called as tunneling states, and through that electrons tunnel and you get high on current. So in SBCNT FET, the transistor action occurs by modulating the transmission coefficient of device. So by changing the gate voltage, we are just changing the transmission coefficient. Okay.
Yes.
Now, what is MOSFET like CNT FET? So this is Schottky barrier, means this metal source and drain are of metal. Okay, but in this one, so this is carbon nanotube and this is doped with N plus and this is doped with N plus. Okay, so when you apply gate voltage, okay, so that gate voltage will reduce the barrier here. So it's mentioned the structure of device is slightly different from Schottky barrier CNT FET, since it is used heavily doped terminals instead of metal. Heavily doped metal, we don't use metal.
Yes.
This device operates on the principle of modulation the barrier height. So we modulate the barrier height basically. Means height of the barrier is changed by this gate voltage. And thus drain current is controlled by number of charge that is induced into the channel. So its operation is just like a MOSFET, CNT FET. Now how it works? So this is your MOSFET, you can see here, and this is conduction band, this is this one. So if you see, this is called as barrier. So these are electrons here, and this is called as barrier. And when you apply gate voltage, this barrier is reduced. You can see here, barrier is reduced here.
Yes.
And these electrons will enter into the source, and they are collected by this drain because
drain source.
Okay, now in CNT FET, what happens? Now this is the barrier you can see here, and here are the electrons. When gate voltage is not there, low, so these electrons cannot jump. So that's why it is having better op characteristics. But when you apply gate voltage, so barrier is still there. You can see here, barrier is still there. But these electrons will tunnel. They will not cross the barrier, but
they will just tunnel it.
Yeah. And that's why you will get better on current and better off current. Means low off current and
low off current, better high on current. Okay. So leakage also is less.
Yeah. And this is basically what it is. So if you see here, this is your MOSFET equation in which mobility depends upon mobility. It depends upon W by L. It depends upon charge. It depends upon voltage, right? So
Yes.
but in case of CNT FET, this is the equation. Let us not understand too much. But if you see in this equation, there is no dependence on W by L, whether it is small or large, and
Yes,
no
yes.
mobility dependence because it is a ballistic transport.
Yeah, it's finally.
Yeah, and that's the reason CNT FET are giving better performance as compared to standard MOSFET. Now here, this is comparison between MOSFET and this one. This is GC means capacitance, gate capacitance. So gate capacitance is
Yes.
less means speed will be more.
Speed is more.
Then this is drain current. This is 500 microamperes per micrometer, but here
So less.
1500, 3 times more.
More, huh?
So mobility you can see here, 7 into 10 to the power
So
6
yes, a lot.
centimeter per this one.
5.
It is this one.
Faster, yes.
Okay, but it is even though you see here mobility is less, but because of the ballistic transport, it gives us better performance. Okay, and no. Yes. And then here in this slide, so there is a performance of CNT FET inverter, NAND gate, NOR gate. And if you see here, this is blue one is CNT FET, red one is also CNT FET, and green one is also CNT FET for different length. Here, and you can see here CNT FET, it's energy delay product. So energy delay product is better for the CNT FET. If you increase length of the CNT FET just 5 nanometer, okay, then its energy delay product increases. But if its length is less, energy delay product is better. And thus, your CNT FET gives us better performance. So this is the last slide. And you don't have to study any circuits, or you don't have to study any circuits or any application. Only what is the structure of GA FET and comparison between normal MOSFET and other MOSFETs, CNT FET, and as well as this one. So therefore, novel, this is MOSFET, this is FinFET, this is GAA FET, and this is CNT FET. So these are called as novel MOSFET architectures. Okay. So, yes, and in this way, we have completed our module number 1. So we have studied each and everything about MOSFET module number 1. I will show you just what I will show you our plan, and then I will tell you. See, this was our first lecture, right? This is our plan. First lecture, we have seen overview of MOSFET, review of MOSFET operation, and MOSFET capacitance. Okay. Yes, then second lecture, we have studied MOSFET scaling. Yes. Right. Explain what are the various scaling. Yes. Then in third lecture, we have studied short channel effects. Yes. Various short channel effects. Then in fourth lecture, we have seen fabrication of NMOS and PMOS. Fabrication, yes. Sir. In fifth lecture, fabrication of CMOS we have seen. Yes, sir. Then in sixth lecture, we have seen lambda. Yes, sir. Lambda. How to draw that MOSFET architecture. Then in seventh lecture, we have seen FinFET architectures. Explain its working, construction, FinFET. And yes, today we have seen GAA FET and CNT. Yeah. And in this way, we have completed our first chapter, that is review of MOSFET operation and fabrication. So from tomorrow onwards, we will start our second chapter, that is combinational CMOS logic and CMOS. This one, we'll start that. Okay. So do you have any questions? You can ask. Any questions? No, sir. No, sir. Then can we stop here? Yes, yes. सर उसमें से भी इतना ही है, मतलब उसका कैसा मतलब डिस्टिंग्विशिंग वो सब भी है फर्स्ट चैप्टर में. हाँ हाँ बस बस बस
और फिर उसका क्या बोलते हैं, वर्किंग और वो सब
हाँ बस 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 इतना ही है
उतना ही है।
that much.
अच्छा
Yeah.
अच्छा, ओके ओके सर, चलेगा।
And सब I have uploaded all अभी 7th and 8th lecture also I will upload, and I will upload
ओके सर,
recordings also, that whenever you
ओके
want
सर,
you can go through it.
ओके सर, यस, थैंक यू सर।